Delighted to welcome now our next presenters from HMCTS, Steve Newman, and from CGI, Max Holland. Thank you, guys.
Hello, I'm Steve, and I couldn't be more out of my comfort zone. Stood here right now. As initial forays into public speaking goes, the RI is probably not the first place to start, but I'll do my best. So as I said, I'm Steve, and I help look after software development at HMCTS. HMCTS, or His Majesty's Courts and Tribunal Service, for those of you who don't speak civil servant, supports the delivery of criminal, family, civil proceedings in England and Wales, and we look after the tribunals across England, Wales and Scotland. It's a big, interesting organisation interacting with people at critical moments in their lives with quite a unique stakeholder topography. We handle about 4.2 million cases a year, employing about 15,000 members of staff across our courts, contact centres, head office functions, and we interact with more than 10,000 registered organisations supporting over 3 million users. We spent about £2.4 billion doing this in 24-25. Our digital footprint is about 50 plus products, and we maintain about 1.7 thousand code repositories. We have about 300 developers across the estate, and like any large organisation, there's a constant juggling act between improving our services, delivering features, and maintaining code. So HMCTS, CGI, we started to think about how we could free up developers' resources and to focus on what mattered, how we deliver more value, whilst we're ensuring the quality and security of our product. So here we have the obligatory slide that I showed to management to justify doing fun things. We started to look at the time we spent fixing CVEs, common vulnerabilities and exposures, and on the back of a napkin, we did some maths. So if, on average, we spent 5 hours fixing CVEs, we have about 10 CVEs per year across 1,700 repositories. That's a number that was worth pursuing. So detecting CVEs isn't the problem. We have tooling built into our development processes and our pipelines, which is commonplace in software development. What is difficult is managing the juggling act in our development squads between the tensions of continuous improvement, feature development, and maintenance. So the question we asked with CGI was, could we use agentic coding to fix CVEs and free up developer time without losing control? We set a target of 5 days using a easy for me to say, a specification-based approach. We were not vibe coding, creating a process which was auditable and controlled. What we wanted to experiment with is using AI in both the building of something and also within the product itself. We used Codex as the coding agent to design and build the application. Then, once it was built, we used Codex API to power the remediation workflow. So AI was involved in both the process of building and the system itself. So what was the process? Before any dev work started, we built our detailed requirements and then prototype screens to give our agents clear context and boundaries. We then set up a development environment using Codex CLI and VS Code, Visual Studio Code, allowing the agents to read, modify, and reason about code bases directly. To ensure the predictability and repeatability, we created a series of files to guide the agent behavior, the how, the what, and the when. This established a clear workflow. Humans designing requirements and guardrails, agents creating and executing plans to produce working code. That preparation paid off, hopefully, as you'll see. Across the 5-day sprint, we wrote around 3 lines of code ourselves. So that is, we were prompting through the initial prompts, agents, behaviors. Sorry, lost my thread. The outcomes of which we didn't have to interact with. We only had to intervene on 3 lines of code. Everything else was generated by the agent. Now this is the seamless handover to Max.
So I'm just going to run you through the steps we took to get Codex ready for agentic development. So we started by creating an agents file, and what that is a file that contains our core principles, our coding standards, and the tech stack that we were using in this code base. We used the Express.js template from HMCTS, so that was our starting point. Codex reads this file before writing a single line of code, so it acts as its context document. It describes the architecture, development guidelines and coding standards, and the technologies used in the project. So you can think of this as an onboarding guide for the AI engineer. Next, we set up our plans file, and we took this from the Codex website. And what a plans file does is it defines the structure of execution plans or exec plans in the repository. So rather than asking Codex to implement large changes in a single step, we asked the agent to work through a structured execution plan. So defining the purpose of the change, the system context, and the concrete steps to implement it, and how progress and decisions should be recorded. So this gives us a controlled way for the agent to tackle larger engineering tasks. So here's an example of one. It's been cut off a bit, but this shows the purpose, process log, and surprises and decision log all in one living document. The plan describes the work required to add logging capability with database-backed users. So it starts with the purpose and the expected outcome, then it tracks progress as the work is completed, records design decisions, and lists concrete implementation steps the agent follows. So in practice, the agent works through the plan step by step, while the engineers can review the process and the decisions as it goes. So it's a living document, and you can see it updating and marking those progression steps off, and it just helps the agent keep context. Next, we moved on to creating a set of skills. There's quite a lot. So we had it for accessibility, for generating remediation plans, checking the CVE IDs against the API, the general CVE API. But this is our Gov UK design system skill. So here you can see the core guidelines page and route patterns, and even a code example showing exactly how the agent should structure a view. So essentially, a skill is a reusable workflow, and this one tells Codex how to implement UI and templates in this repository using the Gov UK design system, which we were following because we used the HMCTS Express.js template. It also defines the tasks, the inputs, strict constraints, so prefer Gov UK nunchucks over raw HTML, and follow the accessibility and typography rules and the structured output we expect. So the important point is the skill doesn't just document style, it encodes behavioral rules the agent must follow, so generated UI is consistent with the Gov UK design system. And then finally, we gave Codex access to an external knowledge through Model Context Protocol, so MCP. So MCP is an open standard that allows AI agents to connect external tools and data to sources in a structured way. So as we were using the Codex API, or the SDK, you can see here we have the OpenAI developer documentation in MCP server, and that provides read-only access to their docs. And with a simple one-line command, you can just add it into Codex. By connecting Codex to this MCP server, the agent, when it goes off and does its work, can query official documentation directly. So this means when the agent needs guidance, so for example, when we integrated the SDK, it went off and retrieved that information directly from the source, rather than relying purely on the model's training data. So the product. So this is the product architecture diagram. It shows how we moved from a detected CVE to a pull request. CVE data is first collected by Jenkins as part of the normal pipeline runs for HMCTS repositories. When those pipelines run, any detected vulnerabilities are written into a central database. Our CVE application consumes that data and presents it to engineers through the dashboard. So from there, the engineers can select a vulnerability and trigger the remediation workflow. Codex generates a remediation plan in the background describing the Codex SDK generates a remediation plan describing the changes required to resolve the CVE. Engineers review and approve that plan before the system moves on to the implementation. At that point, the repository is cloned and Codex applies the remediation changes, and a pull request is automatically generated. So the engineer then reviews the PR through the normal workflow before merging. So the system automates the mechanical work of remediation, and engineers remain in the control of key decisions. So we use Codex to build the product, and then we use Codex API or SDK in the product. And the next slide's a video, so I'm hoping it plays okay. So here we're looking at the CVE list page. At the top of the page, we have a summary section which provides a quick overview of all currently open CVEs, along with any mitigation plans that have already been generated by Codex. This gives teams an immediate snapshot of the current vulnerability landscape across HMCTS products. And then scrolling down, just below that, we have a table listing all the CVEs that have been identified across HMCTS products and repositories. So the CVE IDs themselves come from a recognized global vulnerability database, and a single CVE can potentially impact multiple products or repositories. So within the table, we can quickly see some important information. For example, we have a severity column, which helps us identify the highest priority vulnerabilities at a glance. We also have a status column, which shows the progress of the automated triage process. And finally, on the right-hand side, we have an actions column, which allows us to view more detail for a specific CVE. So this is the CVE detail page, where we can see more details on that CVE. So there's a CVE score, SLA due date, and other information, which will be populated when we get the response from the Codex API. So if there's no remediation plan, we can trigger one. So now we've clicked to generate the plan. The repository code is sent off to Codex with the CVE information. Codex processes this in the background, and it uses that skill we created to go off and get the information and create a remediation plan, which means it follows a consistent structured output. So in this demo, the time has been sped up, but it took around 5 minutes. And then once this plan has been generated, we're able to populate the additional CVE information based on the Codex API response, such as the main package affected and estimated human time to fix the issue. So scrolling down, we have our plan, which starts with a summary section. This explains the vulnerability and highlights the packages impacted. And then next, we have the recommended upgrade path, which outlines Codex's suggested approach for resolving the vulnerability, so what it thinks it has to do to get things sorted. Oh, so that's the findings section. So that's the vulnerable package and stuff. And then here we have the recommended upgrade plan. So taking in the findings, the recommended upgrade path is what Codex has to do to resolve the issue. And then just below that, we have the implementation checklist, which is the main part. This is where Codex translates the analysis into practical steps that an engineer would normally perform manually. The checklist provides a clear, structured set of actions required to resolve the vulnerability. So as you can see here, the steps include updating the affected packages, using Yarn, rebuilding the system, and where necessary, temporarily forcing the secure version of a dependency to be used. So rather than have an engineer investigate the dependency tree and work out the remediation themselves, Codex has already mapped out the steps. And then just below that, we have the verification steps, which explain how to confirm that the vulnerability has been successfully resolved after the implementation steps have been completed. And then finally, the risk and mitigation section, which highlights any potential issues teams may face or look out for after performing the upgrade. So after reviewing the plan, an engineer has 3 options. They can approve the plan, regenerate the plan, or decline the plan. If an engineer is unhappy with the proposed approach, they can regenerate the plan with additional prompting. If the engineer believes the plan introduces too much risk, they can decline it entirely and revert to manual implementation. And then once the mitigation plan has been reviewed and approved by the engineer, the plan is sent to Codex for execution. Codex then makes the required changes in the background, such as updating dependencies or applying the necessary modifications in the repository. So the code is sent off to the Codex API. The Codex API makes the changes, and it usually takes around, well, in this case, it took around 6 minutes, so we was able to focus on some other tasks. But after the changes are completed, a summary is sent back showing what Codex has done. And then Codex also creates a pull request for us with the proposed changes. So at this point, there's still a human in the loop. Engineers can review the pull request, inspect the changes Codex has made, and then improve and merge the pull request once they're satisfied. So this approach allows us to combine AI-driven automation with developer oversight, helping teams resolve vulnerabilities much faster while still maintaining full control over the changes being introduced. I think that's back to you, Steve.
I think the rocking scales is my biggest and best contribution to software engineering, as you can probably all agree. We estimate writing this solution by hand, it would have taken around 4 weeks, and we got to the same point in 5 days with agentic development. Remediating CVEs has moved from hours, as I made up on the first slide, down to minutes. The unintended value of this week has been the bigger questions that it's raised for us as an organisation. We're now asking ourselves, what does value look like? What enabling actions do we need to take to leverage the technology? What skills do we need? And what does responsible use of AI look like for us? The week helped us to start to take steps towards understanding the implications of the technology, which is moving, as we've all kind of discussed throughout the day, incredibly fast. By experimenting and getting hands-on, we've been better able to understand the strengths, but more importantly, the weaknesses, which will help us inform our organisational thinking going forward. Thank you very much.
Well done, guys.